Hello everyone, my name is Daniel Camps. I'm with the I2CAT Foundation in Barcelona, and I'll be presenting today a paper with title 5G OS, demonstrating multi-domain orchestration of end-to-end virtual RAN services. And this is a joint work with colleagues from Zeta Networks in the UK, from University of Thessaly in Greece, and from Paderborn University in Germany, which we have done within the framework of the H2020 5G Picture project. Let me start with the motivation. We know that HCNFV Mano has developed the reference management framework to manage virtual network functions, which are composed into network services, and HC Mano is able to manage all these network services. But the adoption today of HC Mano is mostly or remains focused on single data center domains. Okay, so this is one thing we're observing. On the other hand, we see that 5G has been designed with softwareization in mind. So what does this mean? In particular, for example, the 5G core network adopts a microservice architecture where all the components can be easily deployed within virtual machines or containerized. And even the radio side, so the G-Node B has been split into several functions. We have the remote unit, and the antennas, of course, will continue to be hardware, but then we have the distributed unit, which could be virtualized, and we have the centralized unit, which most certainly will be virtualized. So we can look at the 5G network and we see it as a distributed cloud. It's a distributed cloud that it's going to be hosting all these virtual network functions that compose the 5G core and the radio side, but also application level functions that, for example, can be collocated into an edge computing node. So within this framework, the automation of the provisioning of end-to-end network services that span a single data center domain that can go into different compute domains that are connected through SDN networks and that give access to radio functions that are also virtualized. This remains to be an open challenge, and this is the main challenge that we try to address with the 5G OS design. Let's see what is the 5G OS concept in a nutshell. So first, if we look at the lower part of this figure, we try to represent in an abstract way what we understand as a domain. A domain is can be decomposed into a set of course, infrastructure resources, and then we can have an NFV Mano stack that's going to be managing the compute resources in that domain. We can have SDN controllers or other type of controllers. We could have radio controllers controlling the transport and the radio infrastructure of this domain. And we can then have a domain orchestrator that is deploying services along these different resources within one domain. So we see the proliferation of such domains, and sometimes they even have different orchestration technologies, or some of them will go with an NFV Mano stack based on one approach, with an SDN controller based on one implementation or a different one. So what we were after was to how to solve the problem of interconnecting these domains, and we came up with a lightweight orchestration layer or multi-domain orchestration layer, where the key component is what we call the multi-domain orchestrator, or MDO, that is going to take the logic of the end-to-end service that needs to take resources from these different domains, and it's going to decompose these end-to-end services into the appropriate calls for each of the component domains. So let's look at an example instantiation of the 5G OS. We can have a complex infrastructure like the one shown in the figure, where we have different compute domains. For example, there is an edge domain here, there's an edge compute domain here, there's a central office that could be a micro compute domain, and there's another data center here. Okay. At the same time, we can have different wireless infrastructure. So, for example, here we have a set of small cells. We have here macro cells. Okay. And then we can have a heterogeneous transport network connecting these different infrastructure domains. We can have wireless backhauling connecting the small cells. We can have an Ethernet transport network going from the remote units into the data centers. So the MDO is going to be sitting on top of this, interfacing with the different controller domains. So in particular, we define 3 types of interfaces, namely the MDO Mano interface. So we have here an example of an MDO Mano interface between the MDO and this edge compute domain. We have another instantiation of the MDO Mano interface between the MDO and this other compute domain. We're going to have an MDO1 interface because we need to be able to provision end-to-end services, and we'll explain later the characteristics of this interface. And then we can have one or more MDO run interfaces. So in this case, we have an MDO run. In the case where we have a run controller, we have a run domain controller that can expose services through usually a REST-based interface towards the MDO. So let's look now at the different technologies that we have used in the validation of the 5G OS. So starting with the compute domains, we'll be considering compute domains that implement 2 types of orchestration technologies. The first one is an open source Mano. It's a widely known NFBO supported by ETSI. And the version we used in our validation was release 4, so today OSM is more advanced, it's in release 7, and supports both cloud native orchestration through container network functions and virtual network functions, so VM-based orchestration. In the version that we use, we only focused on the VM-based orchestration for the OSM domain. And then we use a different technology. It's a custom technology developed by University of Paderborn. It's called Pishahang. And it's an orchestration technology that can handle both Kubernetes and OpenStack type of VIMs. Okay. On the wireless side, we're also going to consider 2 different types of technologies that can be virtualized. So the first one is a custom technology that enables Wi-Fi and multi-hop mesh virtualization. And here you can see some details. You can find more information in the paper. So basically, this is the type of platform that is used to develop this technology, a single board computer and a set of modems, Wi-Fi modems. And then the technology instantiates inside the host platform a software-defined data plane. So these are a set of software bridges that allow to take traffic from the different multi-interface boxes and forward it into the transport network. And finally, we have a management plane for this technology that constitutes the RAN controller that is going to interact with the MDO. So in the bottom here, you can see an example of what type of services can be provisioned over this wireless technology. So I could have a set of boxes like the one shown up here. So we have here a linear topology with different boxes where they have access interfaces with the 2x2 MIMO antenna shown here. And then we have some directive antennas here that are used for wireless backhauling purposes. So the MDO can then provision wireless services on top of this infrastructure. For example, saying that I want to deploy a service that is going to be radiating a Wi-Fi or virtual Wi-Fi access point in this box here, okay, in this other box here, and in this other box here. And at the same time, a wireless multi-hop path is set up in order to forward the traffic from these nodes here until the one that has connection to the wired network here. The other type of virtual wireless technology that we consider in the validation of the 5G OS, it's virtual LTE based on open air interface. So in this case, the open air interface or the LTE base station is decomposed, or the LTE, let's say, network is decomposed into a set of virtual network functions. We have 2 VNFs for the base station with one distributed unit and centralized unit, and another VNF for the core network. And these technologies can then be deployed this LTE network can be virtualized by deploying the VMs on top of a compute domain. So one important point to realize is that we are looking at two different types of RAN virtualization here. In the first case, on the Wi-Fi, we have a set of physical network functions that we have a controller that allows an external entity to deploy different virtual services on top of these physical network functions. Whereas in the other case, we have a completely virtualized RAN technology that is deployed using NetCNFV approach in the same way that you could deploy any other type of virtual application. Let's look now at the transport domain, where we have the MDO1 interface that is going to allow the MDO to set up end-to-end connectivity services that, as we have shown at the beginning, can be deployed over heterogeneous transport technology. So to do this, what we're doing is we are leveraging work that was done in the H2020 5G Xhold project, where a hierarchical SDN control plane was defined. So the idea of this control plane is that we have in the data plane a set of devices. So we have devices like this one here. It's what we call transport nodes. These are devices that are not aware of what is connected at the edge of this network. They simply forward packets through pre-provisioned label switch paths, and we can have different control plane areas. So managing, for example, this set of transport nodes, we will have what we call a layer 0 controller. We can have different nodes, different transport nodes for different technologies that will be managed by another technology-specific layer 0 controller like this one here. Now, joining the different technology domains, we have a function here that we call inter-area transport node, whose job is to stitch or bind label switch paths from one domain to the other domain in order to be able to set up an end-to-end connectivity service. And finally, we have another type of nodes in the data plane that are the ones that connect the virtual network functions, like these ones here, to the transport network. And these nodes, we call them edge transport nodes, and are the ones that are going to bind the VNF state into the appropriate label switch path that will take the traffic through the heterogeneous transport network. Then, in order to be able to set up paths end-to-end, since the L0 controllers only have visibility of their domain, we need a higher level of control through what we call the L1 controller. Okay, and finally we have the so-called top controller that in this case is a role taken by the MDO. Now, how do controllers communicate to each other? Several protocols could be used here. In our case, we use a customized version of the control orchestration protocol, or COP. To complete our discussion on the technologies managed by the MDO, we introduce now the dynamic slicing engine, which is a novel tool that can be used by transit providers to offer more control to their customers. So in the example we gave in the previous slide on the heterogeneous transport networks and how can they be controlled through the hierarchical control plane, we were assuming that a single administrative entity is in control of the L0 controllers in the different technological domains. But in practice, if you want to connect distributed data centers, often you'll have to go through a transit provider. And a transit provider will only give you a connectivity endpoint. It will not give you any control on how the traffic is forwarded over his infrastructure. So the dynamic slicing engine allows a transit provider to virtualize his infrastructure and to offer an open flow based endpoint to its customers. So an example here is given through this figure, where we see a set of physical devices, in this case edge core switches, that would be controlled by the provision and managed by the physical transit provider. And when a service is set up, which could be set up through the L0 controller that in this case is managed by the entity hosting the MDO, then a set of open flow endpoints, APIs, are set up here on top of the physical network switches that gives the customer the illusion that is controlling physical infrastructure. So based on the technologies presented in the previous slides, we can now introduce an end-to-end testbed that we developed to validate the 5G OS concept. So this testbed is composed of 4 main domains. So there is one domain in Spain. This is hosted by I2CAT, where we have 2 types of technologies. So we have here the Wi-Fi RAN controller technology that was presented before, and we have here also a transport network segment managed using OBS-based switches. Also providing access, but in this case not the Wi-Fi access but the virtual LTE access, we have another domain in the NITOS testbed hosted by the University of Thessaly, where we have SDRs and we have compute nodes that are managed through OSM and can host the virtual DU and virtual CU functions of the eNodeB. Then we have another domain in Germany, in this case hosted by the University of Paderborn, where this domain has a set of compute nodes and of course a transport domain as well here, managed also with OBS-based switches. But the compute domain is in this case using Pishahang as orchestration and can host both container-based functions and virtual machine-based functions. And finally, we have another domain in the UK. This is provided by Zeta Networks that implements the dynamic slicing engine technology that interconnects the different wireless access and core network domains from I2CAT and University of Thessaly towards University of Paderborn. So having presented our multi-domain testbed, we can now introduce the end-to-end virtual RAN services that we will validate on top of the presented infrastructure and that will be managed by the 5G OS. So we will have 2 services. One is the end-to-end Wi-Fi service, the other is the end-to-end LTE service. So the end-to-end Wi-Fi service is going to have a virtual Wi-Fi service defined in the I2CAT domain, as I was presented before, including the virtual SSIDs and the wireless mesh paths. And it's going to have the core network instantiated in Germany in the domain hosted by University of Paderborn using Pishahang. And in this case, the core network is going to be represented by a DHCP server running inside a Docker container. And to connect the wireless access with the core network, we're going to provision an end-to-end connectivity service through the transport I2CAT domain, the Zeta network transit domain, and the UPV domain. On the other hand, the LTE service is going to be based on virtualized open air interface, DU plus CU functions that will be deployed at UTH in Greece. And the core network is going to be this time VM based, not container based, and it's going to also be deployed at UPV. And we'll have as end-to-end connectivity service, the connectivity, the connections going through the UTH domain, the Zeta network domain in the UK, and the UPV domain in Germany. We can now look at the end-to-end signaling flow to set up the virtual Wi-Fi service. As a first step, the MDO will interact with the RAN controller in the I2CAT domain to set up a new Wi-Fi multi-hop service, defining the service ID, the SSID in this case, and the transport VLAN that will be used to transport the packets coming out of this service. The RAN controller will return to the MDO the MAC addresses of the devices that are authorized to connect to this service. Similarly, the MDO will interact with the compute domain in the University of Paderborn through the Pishahang orchestrator, providing the ID of the network service that needs to be deployed, as well as the transport VLAN. And the Pishahang orchestrator will return to the MDO the MAC addresses of the virtual machines, in this case containers, that need to be deployed. Armed with these MAC addresses, that are the MAC addresses of the endpoints, the MDO will trigger an end-to-end path between the I2CAT and the UPV domains by interacting with first with the ETN controller. The ETN controller will then interact with the L1 controller to set up the end-to-end path between the ETN at the I2CAT domain and the ETN at the UPV domain. the L1 controller will resolve the different domains that need to be traversed, meaning the I2CAT domain, the Zeta Networks domain acting as transit provider, and the UPV domain, and will start triggering the setup of dedicated connectivity services in each of these domains, interacting with the different L0 controllers of each domain. The L0 controllers will then return the IDs of the connectivity services in the individual domains, and the L1 controller will forward these IDs back to the ETN controller. Armed with this information, the ETN controller can now program the ETNs in each domain in order to bind the traffic coming from the VNFs, looking at the MAC addresses, into the appropriate LSPs, label switch paths, based on the identifiers provided by the L1 controller, and can also program the inter-area transport nodes between the I2CAT and the Zeta Networks domain, and the Zeta Networks and the UPV domain. After all this signaling is in place, then the ETN controller will signal through the MDO1 interface to the MDO that the connectivity is ready and traffic can start flowing. Let's look now at how traffic is flowing in the user plane. So we have first here on the left-hand side the I2CAT domain, the wireless service, that is the ETN node, and the I2CAT transport domain. Then we have the inter-area transport nodes and the Zeta Networks domain, and then the UPV domain as well. So through different packet captures, we show that traffic on segment number 1 between the user device and the wireless service is just regular Ethernet traffic. If we look at point number 2, we'll see that the wireless service has included a VLAN tag identifying the service ID, because the ETN can be handling traffic from many different services. So based on this VLAN tag, then the ETN is going to include a new outer Ethernet header into the packet, as we can see here, which has a label switch path, a VLAN identifying the path that this packet needs to follow inside the I2CAT domain. The inter-area transport node is going to match on this label switch path, and it's going to translate it into the one used in the Zeta Networks domain, which will then route the packet based on this label switch path until the UPV domain, where again the inter-area transport node has switched the VLAN towards the one provisioned by the L0 controller in that domain. After reaching the destination ETN, that is the one at UPV, the outer header is removed, and we have again a packet that looks like the packet generated by the user device with the end-to-end service ID, in this case VLAN 10, which will be removed by the ETN device to then deliver to the core network, in this case the DHCP server, the standard packet generated by the user on the I2CAT side. So based on the described testbed, what we did was to evaluate the service provisioning time required to provision this end-to-end Wi-Fi and virtual services. So we've broken this into the different component technologies, and we start by looking at the time required to set up the virtual access networks. So on the left-hand side, you can see a CDF of the service provisioning times for the Wi-Fi service in red and for the LTE service in blue. You see the LTE service goes up to 40 seconds, whereas the Wi-Fi service is always below 5 seconds. The reason the Wi-Fi service is much faster, it's because the service provision is done through the API calls provided by the RAN controller that simply performs certain configuration into the physical network functions, whereas in the virtual LTE service, a full virtual machine needs to be containing the open air interface implementation, needs to be instantiated on top of the open beam used in the UTH domain. The right-hand side depicts the similar metrics for the core network. Both core network components are deployed in the UPV domain, and we see again that the Wi-Fi component is much faster, whereas the open air interface core network takes longer to instantiate. In this case, reaching almost 2 minutes. The reason for that is that the core network function on the Wi-Fi side is deployed inside a container, which is very quick to boot, whereas the OpenAir interface is deployed as a virtual machine on top of OpenStack. We now look at the end-to-end connectivity service provisioning time through the MD01 interface. And we evaluate an end-to-end connection between the I2CAT and UPB domains, that's the blue line, between the UTH and I2CAT domains, that's the red line, and between the UTH and UPB domains, that's the yellow line. Remember that all these end-to-end connectivity services go through the transit domain implemented by Zeta Networks. And we see that we have provisioning times in the order of up to 15 seconds. To complement this view and to understand the reasons why this time is significant, we look at the time required by the L1 controller to program the ETN and inter-area transport node devices along the different domains. And we see these times are really reduced. It's less than half a second, so up to 400 milliseconds. Digging deeper to understand the reasons for the provisioning times across the multi-domain transport network, we look now individually at each domain. So provisioning a path inside the I2CAT domain is depicted as the blue line, inside the UTH domain in Greece is the red line, and inside the UPB domain is the yellow line. We see that in all cases the provisioning times are very quick, so again less than half a second. On the other hand, the graph on the right shows the provisioning times over the transit provider. Okay, and this is the one where we see that provisioning times go up to 15 seconds, and therefore this is the reason for the end-to-end provisioning time measured in the order of seconds. The difference between these three domains and the Zeta Networks domain is that the dynamic slicing engine technology. So in the two cases, what's happening is very different. On the left-hand side, when issuing the end-to-end, the programming of the connectivity service inside the same domain, the controllers are directly attacking the physical devices and programming the rules using OpenFlow, whereas in the case of the transit provider, when a connectivity service is requested, what happens is that a whole virtual topology is set up, providing these OpenFlow endpoints for the customer, and that's why this virtualization requires an order of magnitude higher times for provisioning the connectivity service through this domain. Finally, we can put together all the results from the previous slides to show the end-to-end provisioning times through our multi-domain testbed for the virtual LTE and virtual Wi-Fi services, including configuring the wireless access networks, deploying the virtual machines, our containers in the different domains, and connecting all these components through the multi-domain transport network. And we see CDF showing results around 30 and 40 seconds for the virtual end-to-end Wi-Fi service, and between 90 and 180 seconds for the virtual LTE services for the reasons that we have explained before. Overall, we think the KPIs obtained are very promising in order to automate the provisioning of end-to-end virtual RAN services over 5G infrastructure. So to conclude this presentation, we explained that presented the design of the 5G OS that enables the automated provisioning of end-to-end virtual RAN services across different compute, transport, and RAN domains. We have demonstrated our design through a multinational testbed comprising all these different domains, and we have demonstrated that end-to-end services can be deployed in less than 3 minutes. Our future work will focus on demonstrating how this end-to-end service provisioning can scale when we consider much larger network topologies than the ones we consider in this paper. Thank you very much for your attention.